Okay, this is probably the theorem that you're intended to use for this problem. It's the first theorem on bounds for real zeros of polynomials. And to use this theorem, your polynomial function with real coefficients has to have a positive leading coefficient. And then there's two cases, and you're going to synthetically divide by, in our case, integers, because we're looking for smallest upper bound and largest lower bound on the real zeros that are integers, I believe it says, yes. So we'll go to you can read 1 and 2 here, but we'll go to the next boards and talk about what the theorem means. So here's f of x, but the theorem says the leading coefficient has to be positive, but you can see that if I take g of x as the opposite of f of x, that those functions have the same zeros, negative 1.6 and 3.77. So we're going to use 1, negative 5, 4, 9, negative 25 as the coefficients for synthetic division. And for part 1, we want, you can see that the zero is, one of the real zeros is at 3.77. So just to show you what happens if I try synthetic division by 6 and 4, what the theorem says is that if you do synthetic division by 6, bring down the 1, multiply and add, if these numbers are all positive or zero, then C is an upper bound. Well, if 6 is an upper bound, maybe 5 is too. 1, yeah, they're all positive. So it looks like 5 works. 4, however, gives you a negative number here. And so we cannot use this theorem to say that 4 is the least upper bound, even though it is. If we go to board 4 and look for the largest lower bound, we think that it's going to be something like negative 2. So we think the interval from negative 2 to 5 will contain all the real zeros. But let's try negative 3. If we do the signs alternate in the third row? Positive. By the way, this leading coefficient will always be positive because we have a leading coefficient that's positive. And so do they alternate? Positive, negative, positive, negative, positive. Yes. So negative 3 is a lower bound, but maybe negative 2 is. And positive, negative, yes. Okay. But if we try negative 1, they don't alternate because we get a negative 1 followed by a negative 24 here. So that's kind of the process you go through if you're going to use this theorem to find least upper bound and greatest lower bound for the real roots of a polynomial function. There you go. Hope that helped. If you have any questions, post a comment.